My time. You had your time. Uh, the first thing, this isn't ideal, I know, but I don't have office hours this afternoon or tomorrow afternoon. These are the last two I have to cancel. Um, so no office hours Wednesday or Thursday. Um, if you email me questions about homework problems, I'll try hard to answer them. If you send pictures of your work, just snap a picture of it and send it. It's easier for me to, like if you, no office hours Wednesday or Thursday. If you just send me a message that says like I'm confused about, you know, what you do with the mass on, yeah, number 17B or whatever, then like when I answer the question on my phone, I have to make a mental note to check it on my computer and go, you know what I mean? So if you take a picture of specifically what, I can probably answer it as soon as I see it. Um, but these should be the last two office hours that I have to miss this semester. We're in the last week of hiring interviews for the math department, so that's what I'm doing. Um, Anybody have any homework questions? Okay. Well, we almost finished this example last time. Um, the problem looked like this. You have a hinge connected to a linkage like this. Um, the bottom pin slides in a slot. Um, and there's a 600 Newton force there. And at this instant, well, the lengths are both 3 meters. The masses are both 10 kilograms. At this instant, neither of these two things are moving. Um, and if I label this one body 1 and this one body 2, and the joints A, B, and C like this, we wanted to calculate the acceleration of the pin at C. That might be being used to drive a gear or something, but there are plenty of engineering reasons why you would want to calculate the acceleration at a point like that. And we went through um, all of the calculations. We just didn't solve the final matrix. So what I got when I went through the matrix calculation is that F12 was negative 223.3, no, negative 2.3, 183.6. That's newtons. Alpha 1 was 7.23 radians per second squared. RC, so that's the normal force that the slot's applying to the pin at C, was negative 168.1 newtons. And that doesn't mean much if you don't know how I chose the direction of that normal force, but um, I chose the default direction of it this way, so that it says that it is a force of 168.1 newtons going that way. Which makes sense if you know, think about what direction these forces would act. And then the acceleration of the center of mass of body 2 is 5.42 in the x direction, negative 28.17 in the y direction, meters per second squared. And then alpha 2, the angular acceleration of body 2, is negative 7.23 radians per second squared. The relationship between the two angular accelerations is something you'll see in a few of the problems. So look at this, the way that this linkage is set up, these two have the same length, right? So no matter what these angles are at, you know, whether it's flat or pulled out, at any instant that has to be an isosceles triangle. Those two lengths are the same. And well, since this is horizontal, that means that those two angles have to be the same at every instant. Okay? And if they have to be the same at every instant, they have to be changing at the same rate. So the angular velocities have to be equal and opposite. You know, the changes in those angles have to be the same, and then they have to be rotating opposite directions. And you know, use that reasoning one more time, and the same thing has to be true of the angular accelerations. So we didn't use that as a constraint mathematically, but it comes out in the math if you do your constraints right. You could come up with a simplified way of doing this with a few, you know, I guess you could reduce at least one variable by requiring that relationship. That would take some thinking, and I try to avoid thinking and just do the steps, and that's what I think you should do too. But if you're curious about it, see if you can figure out how to fit that in there. Excuse me. It is kind of nice to have that as a check at the end. Anytime you have one of these triangles where those angles have to be the same just because of the geometry, check your angular accelerations at the end and make sure that it's working that way. All right, let's draw the free body diagrams and stuff. Well, let me answer the question first. So the question was, what's the acceleration of that point C? And so the acceleration of the point C relative to the ground is equal to the acceleration of the point C relative to the center of mass of body 2 plus the acceleration of the center of mass of body 2 relative to the ground. This is circular motion, so that acceleration comes from alpha cross r plus omega cross quantity omega cross r. And this one is our variable A2. So we just add that on at the end. One of our constraint equations was that this in C, at this location C, there can't be x acceleration. And so when we plug our values into this expression, we need to get an x value that's 0. If we don't, then something went wrong. But when you calculate this, what I got was 0 for x. I think it was like negative 0.0025 or something. You know, there's going to be some round up error, but basically 0 there, and then negative 37.56 for y. And so at this instant, if you apply this force here, this is going to accelerate down at 37.56 meters per second squared. Let's also, before I stop this, think about the total loads on this body now that we've calculated all this stuff. Well, we didn't. Okay, so on body 1, we didn't calculate this yet. We don't know what that is yet. We have a downward force of 98.1 there. And then the other end at B, we have two forces acting. We're assuming that the pin is part of member 1. That was the sort of bookkeeping decision we made. And so over here we have the force on 1/2. That's negative 222.3, positive 183.6. And then we also have a 600 Newton force that way. Yeah. And so I'll redraw this. We have the force RA over here. We have the weight force down. And then since the 600 Newton force and F12 act at the same point, that's just a single force vector. So we can think of that as a vector of positive, what's that, 371.7, 183.6. Is that right? Did I do that right? Oh, yeah. $77.7. I'm not going to do it, but how would you calculate RA if so? Why don't we know that, first of all? How did that not come up in our equations? Yeah, because when we isolated body 1, we didn't use Newton's second law. That's never part of the steps that we follow. And so we just use the rotational equation, and our about point is at A. And so that doesn't produce any moment. And so that doesn't show up in the equations, even though it's acting on the body. And that'll always be the case for the body with the fixed point. But if you did want to calculate that now, you would use Newton's second law and go back. Now that you know what you're looking for, use Newton's second law and you can calculate that force. And now you could represent the acceleration of the center of mass in terms of the angular acceleration. So these would be unknowns and you can calculate it. Okay, what about the other body? Okay, so up here, the only force at B on body 2 is negative F12, F on 2 by 1. So that's positive 222.3, negative 183.6. And then you have the downward weight force of 98.1. And then you have the reaction force at the wall with the opposite direction of what we said originally, with a magnitude of 168.1 newtons. And so now if you wanted to, for the people who are taking deform or who've done mechanics and materials type stuff before, if you wanted to figure out something about stresses and strains inside there, you can just, now that you've calculated those forces, you can just ignore the accelerations and stuff and just do the beam analysis on this member now. Assuming, like, now you can just assume that it's a statics problem. Yes. Right. That's right. Any questions about that example? All right. Well, the next topic is back to particle kinematics. So we started out with particle kinematics, then we did particle kinetics, then we did rigid body kinetics. Now we're going back all the way to like the beginning, particle kinematics. But when we did it before, we did it in non-rotating coordinate systems. Now we're going to deal with rotating coordinate systems. So we already covered this, already did this in a non-rotating coordinate system. But there are a lot of times where it's helpful or necessary to use a rotating coordinate system, and it complicates things a lot. So I want to first just sort of explain mathematically a little bit and intuitively where the problems come from, where the difficulties come from with this. So first of all, the laws of classical physics only apply in inertial coordinate systems. So that means the coordinate systems can't first have accelerating origins or second have they can't change axis orientation over time. So that's rotation of the coordinate system. If you have either one of these, you can't do Newton's laws in that coordinate system. You can correct for these. If you have an accelerating origin, the way you correct for it is you use the relative motion equations. Okay, so you use the fact that the acceleration of the object relative to the ground, an inertial coordinate system, is equal to the acceleration of the object relative to your accelerating one, plus the acceleration of your origin relative to the ground. And so this one's pretty easy. Okay. We've been doing relative motion stuff like this whole class. This is the harder one. And this is what we're getting into now. Okay, so I'm going to try to illustrate by this I mean a rotating coordinate system. So why does a rotating coordinate system not work with the laws of physics? I'm going to do it mathematically, kind of. Just we'll identify where the problem is. And also just intuitively. So mathematically, the problem comes about when you take time derivatives in your coordinate system. Time derivatives of any kind of vector in your coordinate system. So remember, in a non-rotating coordinate system, the simpler case, say you want to take the time derivative of a vector u, and this vector u can represent anything. It could be a velocity or a position or anything else that's a vector. So it could be a force or anything. We don't usually take time derivatives of forces, but this is true of any vector. So this is the time derivative of a vector with these components. And in a non-rotating coordinate system, how do you take that time derivative? So what's this equal to? This was like the first week or something. We went through some stuff like this. Yeah, it's just the derivatives of the individual components. And you can rewrite this as ux dot times I plus uy dot times j plus uz dot times k. It's just another way of writing it. Okay. But in a rotating coordinate system, if you take the time derivative of this vector, I'm going to think of it as ddt of, and I'm going to start by writing it out as ux times I plus uy times j plus uz times k. And if you take the time derivatives, you get ux dot times I, but then you have to use the product rule. And so each one of these gives you two terms. And if I separate this out, I can write this as so we can think of it as ux dot uy dot uz dot plus ux times I dot plus uy times j dot plus uz times k dot. And this set of terms is what, causes the difficulty. Because what are those things? I dot, J dot, and K dot, like how are we going to represent those in terms of values that we're given in a problem? Okay. All right, so let me just try to help you kind of get your bearings on this. So notice whether you're in a rotating coordinate system or not, you're doing the same thing when you take a time derivative. Okay. You start out with this thing, these components times the unit vectors in the direction of the axes. And derivatives always require the product rule. So you get this whether the coordinate system is rotating or not. It's just the issue that if the coordinate system is not rotating, then I, J, and K aren't changing in time. And so these extra terms go away. These things are equal to 0 in a non-rotating coordinate system. Okay. When the coordinate system's rotating, these aren't 0. And so we're going to have to deal with it. That's the difficulty. Yep. Yeah, well, we're going to see that you can represent it in terms of the angular velocity of the coordinate system compared to the reference, the ground coordinate system. And that's going to be like the big result that'll let us do all the rest of the stuff. That's the result that everything will be derived from. But when you first glance at it, you just have no idea how to deal with that. So, any other questions? Okay. So now intuitively, I want to just try to give you a sense of why you can't just use accelerations measured in a rotating coordinate system and plug them right into Newton's laws and just go on from there. Um, so why don't kinematics calculated in a rotating coordinate system work in the laws of physics? Okay, so let's think about an example. I hope I didn't already give this whole example earlier. I get so excited when I think of it in the first week of class. Sometimes I draw it, but uh, if you didn't understand what I was talking about the first time, here's a second. Okay, so here's an astronaut in training, future astronaut, hoping to be a future astronaut. And he's doing this thing where the seat whips around. Uh, he's like, why isn't anyone else's chair doing this? Um, and let's think about two coordinate systems. They're both at this instant that I have drawn here. They're both oriented like this, okay? But we're going to consider two coordinate systems. The first one is fixed at the axis. You know, it's not rotating. The second one is rotating with the arm. And that means that the passenger person is always uh, along the negative x axis. So in the first coordinate system, just at the instant we're considering, the person just happens to be in the direction of the negative x. And the second one, that's moving with the arm, and so at any instant, the person's position is the length of that arm in the negative x direction. Okay. Okay, so what are the frames of like a film strip or whatever? Frame, are they called frames? Okay, so 3 consecutive film frames. So for coordinate system 1, I'm going to do first. Those are frames. Okay, in coordinate system 1, what do these film frames look like? So this is the one where it's not rotating. Here's the film strip. Okay, in the first frame, you just see the passenger coming into the frame, right? In the second frame, the person's right in the middle of the frame. And then in the third frame, the person's just leaving the frame, right? Based on those three measurements, you can calculate a non-zero acceleration. Okay, you can see that the person's moving. If there's no tangential acceleration in the motion, if this is a constant speed, then you still see that there's angular velocity. You know that there's a length, so you can calculate the centripetal acceleration. Okay. Force sensors in the chair. Measure non-zero forces. And F net is equal to the mass times that measured acceleration. Okay. In coordinate system 2, this is the rotating coordinate system. We'll do the same thing. Think about these three adjacent film frames. At the first instant, what does the camera see? Yeah, right. That's the key thing, is that that camera is aimed at the passenger. Oh, that guy has some kind of bad genetic disorder. Okay, so position vector, the measured position vector is constant. So the measured acceleration vector is 0. The force sensors still measure forces. And so if you put these together, the net force that's measured does not appear to equal the mass times the acceleration. Okay. So if you want to use the acceleration you measure in coordinate system 2 in the rotating coordinate system in Newton's laws, you have to correct for that problem. Okay. So to use Newton's laws, with measurements from coordinate system 2, you need to make corrections. That's the same thing if you have an accelerating origin of a coordinate system, you need to make corrections for your measurements, and we do that with relative motion equations. This is going to be a different approach for correcting it, but it's the same idea. We have to correct for what it's not seeing that a ground coordinate system would see. And also notice that, so I gave this kind of mathematical description and I gave this intuitive description. Notice that in both cases, the problem was related to what happens as time changes. It doesn't have to do with the single instant that we're talking about. It has to do with what happens in the immediate time vicinity of the point we're looking at. It's the time derivatives that cause the problems. Okay. Any other questions about this? This is like philosophy, so we can go deep on this one. Okay. Well, what we're going to see the big result. I don't know why it's in quotes, but that's what I'm going to call it, the big result. The big thing that everything in this section is based on is this. If a vector is, let's say this vector, we'll call this vector u. So if a vector u is expressed in a coordinate system that's rotating with angular velocity omega, then the time derivative of the vector u is equal to the time derivatives of the components plus omega cross u. Yep. No, not necessarily. This, we can do this in 3D. So we can go back into a full 3D spatial calculation of this stuff. It was only rigid body kinetics that we couldn't do outside of a single plane. So now we're back to sort of full freedom. And I'm going to write this two different ways. Each way is a useful way to think about it at different times. This is one. Equivalently, u dot is equal to u dot observed. Okay, so to an observer in that rotating coordinate system, that's what they think u dot is. Plus this correction. Okay, so like in that astronaut training example, this means the true uh, the true velocity of that person, of the passenger, that's the time derivative of the position, is the observed time derivative of the position, which is 0 because the observed position stays the same the whole time, plus this correction term. Okay. Any questions about that? I'll give sort of give you a little bit of a understanding of where that comes from, and then we'll start applying that to other things. So to calculate, like, what's the true velocity of an object in a rotating coordinate system? Well, we'll get that from applying this to the position vector. What's the true acceleration vector? We'll get that from applying this to the velocity vector that we had just. Okay, that's all.